Hello, this is Friday's lecture for week 14. Just finishing up chapter 30, so very short lecture about nuclear reactions. And I think we've actually said almost everything that needs to be said about this subject already in the previous lecture, but just wanted to review a couple things and then give you some hints or solution techniques for the problems, for the homework. So last time we talked about this notation where you have X is your parent or daughter nuclide, and A represents the total number of nucleons, neutrons plus protons, and Z is the number of protons. And this symbol X and Z are kind of redundant with one another because there's only one symbol that has that atomic number, which is the number of protons. So when we're doing our nuclear equation reactions, we have to balance three things. And this is similar to what you're already doing with chemistry, with the possible exception of spin. So the first one is that we have to conserve the total number of nucleons. Secondly, we have to conserve the total charge. And thirdly, we have to conserve spin. So here's the pro tip for balancing nuclear reactions, that instead of just writing an N for a neutron or a P, I don't know why the screen's doing that, sorry about that, or or a P for a proton, that we should write it in this electronic notation. So one total nucleon and one proton for a proton, and then 1 0 for a neutron. And that just helps us make sure that we keep our A's balanced and keep our total charge balanced. And then there's some notational weirdness in Cengage. Instead of using E superscript minus for an electron, they use E sub m, and which makes no sense to me. And then for a positron, instead of saying E with a plus subscript, we use E sub p, which sort of does make sense. And then neutrino just gets this Greek letter nu, Greek letter nu notation. Antineutrinos, instead of the nu with a bar over the top, get a nu sub b, which also doesn't make sense to me. But anyway, there you have it. Interesting point or something to note is that the total number of nucleons have to be conserved, but neutrons or protons aren't conserved, because in nuclear reactions we can change one to the other, either a proton to a neutron or a neutron to a proton. And perhaps you know this already, but I would recommend memorizing it. If you don't know it, you have to memorize it, because we haven't really talked about spins, and this is a property that electrons have. In fact, all fermions, maybe you know this from chemistry, all fermions have half-integer spins. All bosons, which are neutrons and protons, have integer spins, and so we need something with half-integer spins, in fact, the opposite of the spin of this electron, to balance the spin. So just to go over this real quick, in this equation, we notice we have one plus charge on the left, and neutrons don't have any charge, so this has to be balanced by a plus charge on the right, which is given to us by this positron. And for this equation, we have no positive charges on the left, but we have a positive charge on the right given to us by the proton, so that has to be balanced by a negative charge given by the electron. And the reason I would say memorize it is just memorize this correspondence of positrons to neutrinos and electrons with antineutrinos. If you want to balance the spin of an electron, you need an antineutrino, and if you want to balance the spin of a positron, you need a neutrino. That's the only thing really that you need to memorize. Okay, so let's go on to some examples. These are taken from the homework that's due today, so I think it will make the homework very easy. The first one is, you have a series of nuclear reactions, and you're asked to identify the unknown nuclide. So this amounts to balancing the equation. So we have, I just wrote in purple here, A and Z to indicate the superscripts and subscripts for our unknown nuclide X. So if I were to balance the total number of nucleons, I'm going to take this unknown number of nucleons, A, plus 4 from the helium, plus 24 from the magnesium, plus 1 from the neutron. So I get 25 on the right, and so that means I can solve for A. I get that the total number of nucleons in our unknown nuclide has to be 21. And for charge, note that I'm not saying we need to balance the number of protons. I'm not saying that. I'm using Q for charge, which is what we've been using for charge. And I'm just noting that protons have plus 1 charge, electrons have minus 1 charge, positrons have plus 1 charge, and that is it. Right? Those are all the charges that we need to worry about. And we can't usually, or quite often, this is a counterexample, but we can't just say, oh, because the charge on this left-hand side is equal to 10, that means that the number of protons on the left-hand side is equal to 10. That's only true if this charge is less than the total number of nucleons. And so I'll show you an example where that's not necessarily true next. So in this case, we can get Q equals plus 10 quite easily by adding 10 protons. So we need some element that has 21 total nucleons and 10 protons, and you can look that up on the periodic table, but neon is something that has an atomic number of 10 with an atomic mass of 21. Well, one of the isotopes of neon has an atomic mass of 21. Alright, and then another example in the same problem is we need to balance this equation where we have two hydrogens are being turned into deuterium. And there's something else. There are two daughters that are given off in this reaction. We have to figure out what those are. So let's see if we can deduce it from our conservation of nucleons, charge, and spin. So first, to balance the nucleons, I have 2 times what's going on here, so 2 times 1 gives me 2 nucleons on the left-hand side, and on the right-hand side I have 2 from deuterium, and I don't know how many from this daughter, but I'm just going to call it A, and I don't know how many from this daughter, but I'm going to call that A prime. And since 2 is equal to 2 plus the sum of these two, and they can't be negative, then these both have to be 0. And now let's look at charge. On the left-hand side I have 2 protons. On the right-hand side I have a proton. That means that this combination from the two daughters has to yield 1 positive charge somehow. So here's the example where I've got total nucleons in my unknown nucleides are equal to 0. But I need 1 positive charge. So that means I can't use protons, because if I used a proton, then my A would be not equal to 0, it would be 1. So that means I need something that's got an A equals 0 and a charge is equal to 1. And the only thing that fits that bill is a positron. And then now, so you know, you could have picked either one, but I just said that that's going to be daughter X. Now we have to figure out X prime. And what do we have left? Well, we've got something that with no charge and no mass. Negligible mass. So no nucleons and no charge. The only thing that fits that bill is a neutrino or an antineutrino, and you've memorized that for positron decay you need a neutrino. So that gives us our two daughters, an electron and a neutrino. On the second problem, we are using neutron irradiation of gold to get electrons out. So scanning electron, well, anyway. Okay, so nucleons on the left, I just wrote in the 79 because I looked up the atomic number for gold. So total number of nucleons, 197 plus 1 from the neutron on the left. That means that the total number of nucleons on the right, whatever's in the blank here, has to be equal to 198. I don't get any nucleons from the electron. So, did I already mention that nucleon is called a nucleon because it's in the nucleus? That is a neutron or a proton. So an electron is not a nucleon. Okay. So for the charge, I've got 79 protons on the left, so plus 79 on the left, and a minus 1 on the right from this electron. This is given, it's sort of hidden in the problem statement. It says that if you irradiate gold with slow neutrons, you get electrons out. So we know that electrons has to be one of the things emitted. So that means that whatever's in the blank here has to have a charge of plus 80. And in this case, since you can get 80 protons and still not exceed 198 nucleons, then we can just use, for our unknown nuclide, we can use 198.80. And if you look this up, this is mercury, the atomic number for mercury. Alright, well, one thing left to do is to balance spin, and we know to balance an electron you need an antineutrino, so it means that we have to have mercury plus an antineutrino in addition to the electron on the right to balance it. And the last thing the problem asks you to do is to figure out the energy released, and that's just a binding energy problem like you did in the last section. And for convenience, I just wrote down the mass of the neutron, mass of gold, and mass of mercury, and the conversion between atomic mass and energy, so you can do that part quite easily. And lastly, it's another binding energy problem, but it's asking you to look at how much energy is released during the fission of U-235. And this is what you did last section. To find the energy released, you find the difference between the products and the reactants. So here is the sum of the, actually I did that the other way around, sorry. The sum of the reactants minus the sum of the products. And once you determine that distance, here, all this is given, right? You have the mass of the neutron here, you have the mass of 235. Barium and krypton are given in the problem statement, so all of these masses are given. If you use this for mass of 235, so you can figure out the heat released. Capital Q is heat. And the second part of the question asks you, what is the fraction released? And so you just take this answer that you got, the Q released, and you divide it by the rest mass of uranium-235, and that gives you the fraction of uranium-235's rest mass that's released as energy. Okay, well, I hope that helps, and that you have a fantastic weekend, and I will see you on Monday.